Welcome back, everyone. You know, if you're focused on understanding the invisible backbone of our modern world, you are in the exact right place today. We're going to look at a fundamentally crucial engineering decision in power distribution, and that is choosing the right cable insulation. Specifically, we're looking at the heavyweight matchup between PVC and XLPE. This single, seemingly simple choice directly impacts a network's reliability, the overall project economics, and, most importantly, safety. Okay, let's dive into this.
Think about it for a second. What actually separates a rock-solid, reliable power grid from a total melting disaster? Well, extreme heat, mechanical stress, and just harsh environmental conditions in general are the absolute enemies of power distribution. When you've got millions of dollars and thousands of lives depending on electricity flowing uninterrupted, the stakes of choosing the right protective jacket for those conductors couldn't be higher. We're not just talking about wrapping some plastic around a wire. We're talking about the literal barrier between functional infrastructure and catastrophic failure.
So here's our roadmap for today's explainer. We've got 1. The molecular showdown. 2. By the numbers. 3. Strengths and weaknesses. 4. Real-world engineering applications. And finally, 5. Passing the test. Let's get right into it.
Section 1. The molecular showdown. Thermoplastic versus thermosetting. This is where we look at the fundamental chemical differences that literally dictate how these materials perform.
Now, what's really interesting about this slide is the concept of vulcanization. See, PVC, or polyvinyl chloride, is a thermoplastic material. Simply put, that means it softens and can actually deform when it gets heated up. But XLPE, it undergoes this vulcanization process. The polyethylene molecules are chemically bonded, or cross-linked, into this really rigid 3D structure. And that essentially turns XLPE into a thermosetting plastic. Once it's set, it is set. It simply will not melt at high temperatures the way PVC does.
To kind of build a mental model for this, think of PVC as your reliable everyday commuter car, right? It gets the standard job done perfectly, and it maneuvers around really easily. XLPE, on the other hand, is like a heavy-duty armored truck. It's built for extreme conditions, taking on thermal and physical abuse that would completely destroy that everyday commuter car.
Section 2. By the numbers, the tail of the tape. It's time for these two materials to step into the ring for a direct, statistical comparison.
Okay, looking at the numbers here, notice how XLPE absolutely dominates when it comes to thermal limits and environmental resilience. I mean, it's got a higher max operating temperature, a vastly higher short circuit threshold, much lower dielectric loss, and excellent moisture resistance. But take a look at that bottom row. This is where PVC really shines, because it is highly flexible, whereas XLPE, while lighter, is considerably more rigid. So let's unpack how that actually translates into real-world performance differences.
First up, the data highlights a really crucial 20-degree gap. PVC tops out at a continuous operating temperature of 70 degrees Celsius, while XLP pushes all the way to 90 degrees Celsius. Now, you might be wondering, why does that matter? Because that extra 20 degrees unlocks a significantly higher ampacity, which is just a fancy word for current carrying capacity for the exact same size conductor. You can literally pump more power through the exact same copper or aluminum wire simply because that XLP insulation can handle the extra heat generated by that current. It's a massive efficiency boost. And this brilliantly illustrates the extreme stakes during a catastrophic fault. If a short circuit happens, you get this immense spike of heat generated in just a fraction of a second. For a maximum of 5 seconds, PVC can withstand 160 degrees Celsius before it starts deforming. But XLP? It can survive a staggering 250 degrees. So in a major fault event, the PVC might melt, causing a permanent, very expensive failure, while the XLP survives to operate another day.
Let's move on to Section 3, Strengths and Weaknesses, Trading Blows. We've seen the raw numbers, but how do these materials actually handle the practical realities of a busy construction site?
Looking at XLPE, its strengths are definitely those high-performance stats: high ampacity, immense thermal resilience, great moisture resistance, and a lighter weight that actually reduces the structural loading on cable trays. But the drawbacks are very real for engineers on the ground. For one, it has a much higher initial procurement cost. And also, because of that 3D cross-linked structure we talked about earlier, its increased rigidity makes routing these cables through tight spaces or complex panel layouts an absolute nightmare for installers.
Now, here comes the classic "it depends" moment with PVC. Because despite XLPE's clearly superior stats, PVC remains incredibly popular. Why? Well, it's cost-effective and it's highly flexible, which is perfect for snaking through tight conduits. Interestingly, thanks to the chlorine and its chemical structure, it is inherently flame retardant. However, its weaknesses are definitely severe. It melts above 70 degrees, its high dielectric losses make it basically useless for high voltage, and, this is a big one, if it actually is subjected to an active fire, that same chlorine causes it to emit dense black smoke and toxic, corrosive hydrochloric acid fumes.
So the crucial point is, where do we actually use them? Let's step into Section 4, Real-World Engineering Applications. This is where the theory meets massive infrastructure. For heavy infrastructure, XLPE is the undisputed champion. If you're dealing with medium voltage networks, so like 11 kV up to 33 kV, or high voltage transmission, XLPE is your go-to, no questions asked. Even on low voltage networks, it's heavily utilized for those main incoming feeders coming off massive power transformers. Basically, if a cable is going into an underground trench, direct burial, or a really harsh marine port environment where moisture is a constant threat, you're using XLPE.
But contrast that with PVC's territory. PVC is restricted pretty much entirely to low voltage and extra low voltage systems. But within that specific arena, it is universally dominant. It's the absolute standard for indoor secondary distribution, residential branch circuit wiring, lighting networks, and control systems. In environments where the thermal demands are pretty moderate and being able to bend and route the wire easily is your highest priority, PVC is exactly what you want. And hey, you don't just have to take my word for it. Strict global standards literally enforce this division. While standard IEC 60502-1 covers both PVC and XLP for those lower voltages, IEC 60502-2, which covers up to 30 kilovolts, focuses entirely on XLP and EPR rubber. PVC is literally excluded from medium voltage applications by the standard. On top of that, regional utility providers like the Saudi Electricity Company, for example, enforce strict codes that mandate XLP entirely for all underground utility routing.
Which brings us to our final stop, Section 5, Passing the Test. Before any of these cables are allowed anywhere near a live power grid or your home, they have to prove their worth in the laboratory.
One of the most fascinating verifications they do is the hot set test, and this is uniquely for XLPE. This test physically proves that the crucial chemical cross-linking process was actually a success. First, they apply high heat to a sample. Second, they hang a heavy mechanical load from it. Third, they measure exactly how far it stretches. It absolutely must stay within strict elongation limits. And finally, they remove the load, and the material has to snap back and completely recover its shape. If it doesn't, the whole batch fails.
And just how hot is that high heat in the hot set test? Try 200 degrees Celsius. They literally bake the XLP sample at 200 degrees while hanging weights from it just to ensure its thermosetting properties hold up. It's a pretty brutal demonstration of resilience for sure. And honestly, that's just one test. These cables also have to survive high voltage dielectric withstand tests to make sure they can handle extreme power surges. They go through insulation resistance testing, where XLP consistently hits the massive giga-ohm range, pretty much blowing PVC out of the water. For higher voltages, they even run tan delta tests and check for microscopic water trees that could degrade the insulation. Only the absolute strongest survive the factory floor.
So what does this all mean for the future? We've seen how vastly superior XLPE is at handling thermal stress and environmental abuse. As our power grids modernize, as electrical demand skyrockets, and as global temperatures continue to rise, will the flexible, cost-effective standard of PVC eventually be entirely engineered out of infrastructure? Will it be totally replaced by the invincible rigidity of XLPE? It's a massive question that every electrical engineer and infrastructure planner is having to weigh right now. Thanks so much for joining me for this explainer today, and keep questioning the systems that power our world.